In the early months of 1985, a rifle arrived at British Army evaluation facilities that represented more than a decade of development work. The L85A1, designated as part of the SA-80 small arms for the 1980s weapon family, looked fundamentally different from the rifles it was meant to replace. Where the L1A1 SLR, Britain's adaptation of the Belgian FN-FAL, extended nearly 44 inches in length, this new weapon measured barely 31 inches. The difference wasn't cosmetic trimming. It represented a complete architectural reimagining of how a military rifle could be constructed. The bullpup configuration, with its receiver positioned behind the trigger assembly, had been theorized for decades. The French had experimented with the concept, the Austrians had deployed the Steyr AUG, and the Israelis were developing the Teva. But Britain's adoption carried particular significance because it came from RSAF Enfield, the same institution that had developed the Lee Enfield, arguably the most successful bolt-action rifle in military history. The transition from that proven lineage to this radically different design signaled how completely modern engagement had shifted the engineering priorities. The rifle that arrived for evaluation incorporated 7 distinct design tiers, each addressing a specific engineering requirement. The bullpup architecture provided the foundational logic, compactness through repositioned components. The gas-operated rotating bolt system, adapted from the AR-18 mechanism, offered a proven method for harnessing propellant gases to cycle the action. The integral SUSAT optical sight replaced traditional iron sights, acknowledging that modern infantry priorities favored accurate first-shot capability over close-quarters instinctive shooting. Polymer furniture reduced weight and manufacturing complexity. Stamped steel receiver construction allowed for economical production. The magazine interface system attempted to provide reliable feeding while accommodating ambidextrous operation. And the trigger mechanism, necessarily extended through a linkage system due to the bullpup layout, had to translate user input from a forward position to the rearward action group. Each tier represented defensible engineering logic. The question was whether they could function reliably when integrated into a single weapon system subjected to the mechanical stresses, environmental contamination, and operator variability of actual service. The evaluation teams would spend months attempting to answer that question through structured testing protocols. But the real answer would only emerge later, when personnel carried these rifles through training exercises, equipment inspections, and operational deployments that revealed vulnerabilities no laboratory environment could fully replicate. The L85A1 represented British ambition to modernize small arms while maintaining domestic manufacturing capability during an era of defense budget constraints. It embodied a specific moment when theoretical advantages, compactness, optical sight integration, manufacturing economy, seemed to justify departing from conventional rifle architecture. Whether those advantages would survive contact with mechanical reality remained to be demonstrated. If stories like this help you see how engineering quietly shaped history, tell us in the comments what surprised you so far, and stay with us for the next chapter. The Royal Small Arms Factory at Enfield Lock carried more than 2 centuries of manufacturing heritage when it began developing what would become the L85A1. Established in 1816, RSAF Enfield had produced the patent 1853 Enfield rifle musket, the Lee Enfield series, the Sten submachine gun, and countless other weapons that equipped British forces through multiple historical events. But by the 1970s, that heritage existed under the shadow of inevitable closure. The British government had decided that small arms manufacturing would transition to private industry, and RSAF Enfield's days as a government arsenal were numbered. This institutional mortality created a peculiar pressure on the engineers developing the SA-80 program. They were designing what would be Britain's standard infantry weapon for decades, yet they were doing so within a manufacturing facility that wouldn't exist to produce it at scale or support iterative refinement based on field feedback. The rifle had to be correct on the first attempt because the institutional knowledge that created it would disperse once the factory closed. There would be no gradual evolution through successive marks and modifications, as the Lee Enfield had enjoyed over half a century of continuous development. The engineering team faced specific constraints that shaped every design decision. The weapon had to chamber 5.566 45mm NATO ammunition, standardizing Britain with Allied forces while abandoning the larger 7.62 51mm round of the L85A1. It had to be producible using stamped steel construction rather than the more expensive machined receivers, because defense budgets couldn't sustain premium manufacturing methods. It needed to accommodate optical sights as standard equipment, reflecting a doctrinal emphasis on accurate engagement at medium range. And it required a bullpup layout to achieve compactness for mechanized infantry while maintaining adequate barrel length for the 5.56mm cartridge to reach effective velocity. Each requirement individually was reasonable. Collectively, they created a design space with very little margin for error. The bullpup configuration, while achieving compactness, necessitated a trigger linkage system that added mechanical complexity and potential points of failure. The gas system had to be optimized for economical manufacturing rather than absolute reliability. The magazine catch, positioned for ambidextrous access in the bullpup layout, couldn't be designed with the simple robustness of conventional rifle magazine releases. The stamped receiver reduced costs, but required precise welding and assembly procedures to maintain tolerances. The engineers at RSAF Enfield were not naive. They understood the challenges. But they were operating under institutional pressure that compressed development timelines and limited the resources available for extensive iterative testing. The SA-80 program had to succeed because there was no institutional future in which gradual refinement could correct initial shortcomings. When RSAF Enfield closed its doors in 1988, 3 years after the L85A1 entered service, the rifle would have to stand on its own merits or reveal its vulnerabilities. Without the benefit of the engineering continuity that had allowed weapons like the Lee Enfield to evolve through decades of institutional refinement, the 7 design tiers of the L85A1 functioned as a layered system where each component addressed a discrete engineering challenge. Understanding how the weapon worked required examining each tier individually before considering how they interacted within the complete assembly. The first tier, bullpup architecture, established the fundamental layout. By positioning the action group behind the trigger, the L85A1 achieved a total length of 785 millimeters while retaining a 518 millimeter barrel. This wasn't arbitrary compactness. It reflected specific requirements for personnel operating in mechanized vehicles, helicopters, and confined urban spaces. The trade-off was complexity. Every control surface, every manual of arms operation, had to account for the rearward position of the chamber and magazine. The second tier involved the gas operation system. The L85A1 adapted the short-stroke gas piston design pioneered in the AR-18 Armalite rifle. When triggered, propellant gases entered a port drilled in the barrel, pushed against a piston that struck the bolt carrier, and drove the action rearward to extract the spent case and chamber a fresh round. The system was simpler than the direct impingement mechanism of the M16 rifle, with fewer components exposed to hot gases. But the gas system required precise regulation to function reliably across different ammunition loads and environmental conditions, and cost-constrained manufacturing left little margin for component variation. The third tier was the SUSAT optical sight, Sight unit small arms trilux. Unlike previous British rifles that relied on iron sights, the L85A1 was designed from the beginning for optical engagement. The 4x magnification sight used tritium illumination that required no batteries, and it was engineered to hold zero despite the vibration and shock of repeated use. This represented a doctrinal shift. British tactics now assumed that personnel would engage targets at 300 to 400 meters with aimed fire rather than suppressive volume. The fourth tier encompassed the polymer furniture, handguard, pistol grip, and buttstock. These components reduced weight and simplified manufacturing, but they had to withstand impact, temperature extremes, and repeated handling without cracking or deforming. The polymer chosen had to maintain dimensional stability across the temperature range, from Arctic exercises to desert deployments. The fifth tier was the stamped steel receiver. Unlike machined forgings, stamped construction formed the receiver from sheet steel that was cut, bent, and welded into shape. This reduced manufacturing time and cost, but it required extremely precise welding procedures and quality control to ensure that the receiver maintained proper alignment under operational stress. Any dimensional variation in the receiver translated directly into bolt binding, feeding malfunctions, or extraction failures. The sixth tier involved the magazine interface system. The L85A1 used a magazine catch positioned for ambidextrous operation, necessary in a bullpup where the magazine sat far back from the trigger hand. But this positioning created mechanical compromises. The catch had to be robust enough to retain the loaded magazine during vigorous movement, yet easy enough to release under stress. The magazine well geometry had to guide magazines into position reliably, even when inserted forcefully at angles. The seventh tier was the trigger mechanism, perhaps the most challenging engineering problem in any bullpup design. The trigger itself was positioned conventionally, but the sear that released the hammer was 20 centimeters rearward. A linkage system translated forward trigger movement to rearward sear release. But this linkage introduced flexibility, friction, and mechanical looseness that degraded trigger feel and consistency. Every millimeter of play in the linkage, every point of friction, translated into unpredictable trigger behavior that frustrated accurate operation. These 7 tiers, designed as integrated solutions to specific requirements, functioned adequately when new and carefully maintained. The question was whether they could maintain functionality when subjected to the accumulated stress of continuous service. Do you think this design choice was inevitable or a risky gamble at the time? Share your view in the comments and pass this story to someone who enjoys understanding how things really work. The initial evaluation reports from British Army trials acknowledged the L85A1's compactness and optical sight advantages, while noting areas requiring attention. But early evaluations conducted under controlled conditions with new equipment and supervised maintenance didn't capture how the rifle would behave after months of service with standard personnel performing normal maintenance procedures. The mechanical vulnerabilities emerged gradually as service expanded beyond specialized evaluation units to general battalions. Reports surfaced regarding magazine feeding issues, rounds failing to strip cleanly from magazines, resulting in stoppages that required immediate corrective drills. The magazine catch, positioned for ambidextrous access, proved susceptible to inadvertent activation during vigorous movement. Magazines would release unexpectedly when personnel maneuvered through vegetation or crawled during tactical exercises. The gas system showed sensitivity to residue that hadn't been apparent in limited testing. The short-stroke piston design required precise clearances to function reliably, but propellant residue and environmental contamination could accumulate in the gas port and piston cylinder, gradually degrading cycling reliability. It was found that the weapon required more frequent cleaning than previous rifles to maintain reliability, But the bullpup layout made field stripping and cleaning more complex than conventional designs. The trigger mechanism revealed another category of issues. The extended linkage system introduced inconsistency that varied between individual units and degraded over time as components wore. Some triggers felt heavy and gritty, while others had excessive take-up or creep. For those trained on the smooth, consistent triggers of the L1A1, the L85A1's trigger behavior was frustrating and potentially compromising to accuracy, particularly for designated marksmen who needed a predictable trigger break for precision. Environmental testing revealed additional vulnerabilities. Sand and fine dust infiltrating through gaps in the design could interfere with the bolt's reciprocating motion. Water ingress during river crossings or prolonged rain exposure affected reliability. Cold weather exercises exposed problems with the polymer furniture becoming brittle and certain lubricants thickening to the point where cycling slowed or stopped entirely. The British Army responded with enhanced training on maintenance procedures, refinements to lubricant specifications, and procedural adaptations, such as taping magazines to prevent inadvertent release. But these measures addressed symptoms rather than underlying mechanical vulnerabilities. The rifle functioned adequately when meticulously maintained under supervised conditions, but that standard proved difficult to sustain across entire formations conducting routine training and operations. By the mid-1990s, after a decade of service, the accumulated evidence had become undeniable. The L85A1 exhibited reliability rates significantly below what modern service required. Personnel had developed workarounds and coping strategies, but those couldn't substitute for fundamental mechanical reliability. The rifle that had represented British ambition to modernize small arms now represented an engineering outcome where multiple compromises, each individually defensible, had combined to produce a system whose reliability under field conditions fell short of requirements. The British Ministry of Defence faced a decision: continue attempting to refine a fundamentally compromised design through incremental modifications, or acknowledge that the integration of the 7 design tiers required comprehensive redesign by specialists with specific expertise in modern systems. The final curiosity of the L85A1 emerged not from what the weapon was designed to do, but from what became necessary after a decade of service revealed its limitations. In 2000, the British Ministry of Defence contracted with Heckler & Koch, the German manufacturer, to conduct a comprehensive redesign program. The resulting L85A2 retained the L85A1's basic architecture: bullpup layout, barrel length, caliber, SUSAT sight, while modifying or replacing virtually every mechanical component that contributed to reliability issues. Heckler & Koch engineers redesigned the gas system with improved components and tighter tolerances. They replaced the original firing pin with a more robust design, less prone to failure. They modified the hammer mechanism to improve reliability. They redesigned the magazine catch to prevent inadvertent release while maintaining ease of operation. They added a new cocking handle with improved ergonomics. They modified the bolt carrier and guide rods to enhance cycling reliability. They upgraded the trigger mechanism to reduce weight and improve consistency. They treated the barrel with a chrome lining to reduce residue buildup and extend service life. The modifications transformed the weapon's reliability. Personnel who had struggled with L85A1 stoppages found that the L85A2 functioned with the consistency expected of modern equipment. The improvements weren't marginal. They represented a fundamental increase in mechanical reliability that validated the basic bullpup concept while acknowledging that the original implementation had fallen short of necessary standards. This outcome revealed the essential lesson embedded in the L85A1's history. Theoretical engineering advantages mean nothing if mechanical execution doesn't achieve reliable function under field conditions. The 7 design tiers, bullpup architecture, gas operation, optical sight, polymer furniture, stamped construction, magazine interface, trigger linkage, were all conceptually sound. The vulnerabilities emerged from how those tiers were integrated within the constraints of compressed development timelines, limited testing resources, and manufacturing decisions driven more by cost than by absolute reliability standards. The L85A1 demonstrated that engineering exists within a narrow margin where seemingly small compromises compound into significant functional deficiencies. A magazine catch positioned slightly wrong, a gas system with clearances a fraction too tight, a trigger linkage with excessive play, stamped components with marginal dimensional consistency. Individually, these might seem like minor issues, but collectively they degraded reliability to unacceptable levels. The weapon also revealed how institutional context shapes engineering outcomes. RSAF Enfield, closing as an institution even while developing the SA-80, couldn't provide the continuous refinement that complex systems typically require. The British Army inherited a rifle that needed iterative improvement, but the manufacturing knowledge and engineering continuity that could have provided that improvement had dispersed when the factory closed. The L85A2 improvements didn't represent entirely new engineering. They represented the application of refined manufacturing standards, tighter tolerances, and component optimization that might have been incorporated into the original design given different constraints. The final curiosity, then, is this. The L85A1 failed not because bullpup rifles are inherently flawed, but because the specific circumstances of its development compressed engineering decisions into a narrow window that didn't allow for the iterative refinement that separates theoretically sound designs from mechanically reliable tools. The legacy of the L85A1 extends beyond its service as Britain's standard rifle from 1985 to 2002. It represents a case study in how engineering, perhaps more than most disciplines, demands that theoretical elegance yield to mechanical reliability proven through extensive real-world validation. The weapon demonstrated that compactness, optical sight integration, and modern materials offer genuine advantages when implemented within a mechanically sound framework. The L85A2's successful service after 2002 proved the bullpup concept viable. Personnel appreciated the shorter overall length during vehicle operations and close-quarters scenarios. The SUSAT sight, retained from the original design, provided engagement capability that iron-sighted rifles couldn't match. The fundamental architecture was never the problem. The problem was execution quality in the original implementation. The L85A1's history also illuminated how institutional factors shape engineering outcomes. RSAF Enfield's impending closure created time pressure and resource constraints that limited iterative development. Modern design requires extensive testing across environmental extremes, ammunition variations, and operator skill levels. Testing that ideally extends across several years of prototype refinement before full-scale production begins. The SA-80 program compressed that timeline, and the weapon bore the consequences through its first decade of service. From a manufacturing perspective, the L85A1 revealed that cost-optimized production methods require extraordinary discipline in quality control and dimensional consistency. Stamped receivers can function reliably. Many successful designs use stamped construction, but they demand precise manufacturing procedures and rigorous inspection standards. When those standards aren't met, or when designs don't include adequate tolerance margins, reliability suffers in proportion to the dimensional variations that manufacturing introduces. The subsequent contract with Heckler & Koch represented more than technical rescue of a flawed system. It acknowledged a fundamental truth. Sometimes institutional pride must defer to specialized expertise. The willingness of the British defence establishment to contract with a German manufacturer to fix a British rifle demonstrated that operational requirements supersede national prestige. Personnel needed reliable equipment, and pragmatic acknowledgement of that necessity mattered more than defending the original design's adequacy. For historians and engineering students, the L85A1 occupies a specific educational niche. It wasn't a complete failure. It served for 17 years before comprehensive redesign, and the improved L85A2 continues in service decades later. But it demonstrates the unforgiving nature of mechanical systems, where multiple small compromises accumulate into significant functional deficiencies. It shows that theoretical advantages mean nothing without reliable mechanical execution. And it proves that development requires iterative refinement through extensive real-world testing, something that compressed timelines and institutional constraints can fatally undermine. The 7 design tiers of the L85A1 represented 7 opportunities to optimize, and 7 points where decisions shaped by constraints produced a weapon that required fundamental redesign to achieve the reliability modern service demands. That outcome doesn't diminish the engineer's efforts. It acknowledges the difficulty of creating mechanical systems that must function reliably under the most demanding conditions humans can impose on manufactured tools. If you enjoy calm, true stories about how engineering shaped the world, subscribe to the channel, leave a like, and tell us from which country you're watching.